Welcome to Chapter 3. In this lecture, we'll discuss Section 3.1, which introduces some fundamental concepts we'll use throughout Chapter 3, along with Section 3.2. In Section 3.2, we will build on the basic concepts of the first section to solve a preliminary form of the ODEs we're interested in this chapter. In the previous chapter, we investigated a wide range of first-order ODEs. We had first-order linear ODEs, separable ODEs, etc. But in this chapter, we move onward and upward to consider second-order ODEs. But we won't be analyzing all second-order ODEs. We'll be focusing on a pretty specific type of second-order differential equations. We'll be looking at second-order linear differential equations. The general structure of a second-order linear ODE can be summarized in this equation. Here I've introduced these functions, a of t, b of t, c of t, g of t, but I'm really just trying to capture the fact that these expressions within the differential equation must be made up entirely of t's, no y's. That's because I'm forcing these ODEs to be linear. So you remember that linear restriction would prevent me from having any y term multiplied by this y, for example. So we have second order. We have y double prime, a y prime, and a y, and then all of the other components of this differential equation must be exclusively in terms of t's. And I remind you that that also includes constants, because a constant would be considered t to the 0th power. This may seem like a pretty restricted class of differential equations, but trust me, there's a lot of interesting and useful stuff covered here. To start the chapter, we'll actually make our focus even more specific. We'll add two additional restrictions. First, we'll force the coefficient functions, a of t, b of t, c of t, to actually just be constants. So we said in general they could be expressions in terms of t. Now we're further restricting them, so we're saying that they have to be just constants. Secondly, we'll force the right-hand side, the g of t expression, to be 0. This leaves us with an ODE of this form here. I have a constant a times y double prime plus some other constant b times y prime plus a constant c times y equals 0. Again, maybe you're thinking that we've narrowed our focus too much, but trust me, there is a lot of information packed into this seemingly simple ODE. Note that I've snuck in a definition here. When we have a right-hand side equal to 0, as we do here, we call this type of ODE homogeneous. This family of ODEs is very important, and as you'll see throughout the rest of the chapter, this family models a pretty wide range of physical phenomena. We'll be working with this type pretty exclusively in this chapter. So we give this type an acronym. These differential equations are linear, and they're homogeneous, and on the left side we have constant coefficients. So we abbreviate the name of this type of differential equations as LHCC. You'll hear me say LHCC a lot in this chapter. This is, as I said, the primary type of differential equation that we'll be working with in Chapter 3. So how do we solve this type of differential equation? I'd like to demonstrate most of the key features by looking at a specific example. For example 1, our ODE is y double prime minus 5y prime minus 14y equals 0. So this has the necessary structure. It's linear, second order. It's homogeneous, meaning this right-hand side is equal to 0. And the coefficients on the left-hand side are all constants. Admittedly, we have been given basically no guidance for how to solve this ODE. But let's think about what this differential equation is saying. It's saying that we want to find a function. We want to identify a y of t that makes this equation true. That is, we want a function which has a property that if we take its second derivative, subtract 5 times its first derivative, then subtract 14 times the function itself, everything cancels out. They all equal 0. What type of function could potentially demonstrate that structure? Could a polynomial? Suppose we started with, say, t squared. When we differentiate, we get 2t, a linear function. Differentiating it again, y double prime equals 2, a constant. Even if we started with a fancier polynomial, differentiating gives me fundamentally different functions for y prime and y double prime. So I don't see how this function with its derivative and its second derivative could be added together in such a way that they would cancel each other out. So that suggests that we want a function that doesn't fundamentally change when we differentiate it. There might be some changes, changes, which will be accounted for by the coefficients here in the differential equation. But fundamentally, the function shouldn't change when differentiated. What function has that property? Say it with me now. An exponential. So, based on a careful consideration of the structure of this ODE, I think it's reasonable to suppose our solutions are exponentials. More specifically, I'll actually suppose y equals a general exponential. So let's say y equals e to the RT. I don't think this will work for just any r value or values. So the goal now becomes to find which specific value or values of r will actually make y equals e to the RT a solution of this differential equation. This is actually a process we've done previously in this class. We just take the appropriate derivatives, y prime, y double prime. We plug those into the differential equation, and then that gives us this expression. Now I can clear out the parentheses. And unsurprisingly, there's an e to the RT in each term, so I can factor that out. And now we know that this e to the RT component is never equal to 0. So no matter what r is, and for all possible values of t, this component is never equal to 0. So I have two things that are multiplied to equal 0. This one is not equal to 0, so that implies that this second factor, which in this case is this quadratic, must equal 0. So that leads me to solve a simple quadratic equation. This particular quadratic factors nicely, and I can pretty quickly identify that the two roots of this quadratic equation are r equals -2 and r equals 7. So note that this actually gives me two separate solutions to my original differential equation. Here I've written those two separate solutions as y sub 1 and y sub 2. I have y sub 1 equals e to the -2t, and y sub 2 equals e to the 7t. And if you felt like it, you could take these specific exponential functions and plug them back into our differential equation, and you would confirm that both of these are in fact solutions to our differential equation. In a sense, it feels like we're done. We've found not only one, but two separate solutions to our differential equation. But on the other hand, it's unclear if one of these is my general solution. If so, which one? Or do I need to somehow incorporate both of these into a general solution? To address these questions, let me continue working with this example. First, note that if I were to take one of the solutions I've identified, say y sub 2, and multiply it by an arbitrary constant, here I've written y sub 3 is equal to c times y sub 2. Y sub 2 is just e to the 7t. So I've created a new function by taking one of my known solutions and multiplying it by a constant. So note that this new function is also itself a solution of my differential equation. Again, here I've taken this new function, plugged it into the differential equation, or the expression on the left. Then after some simplification, it does in fact equal 0. So this new function y sub 3 satisfies my original differential equation. So y sub 3 is also a solution of my differential equation. This is an important general fact. For this type of differential equation, any scalar multiple of a known solution is also a solution. Playing this same sort of game, let me define, say, y sub 4 to be the sum of y sub 1 and y sub 2. These calculations are a little tedious, but if you look over them carefully, you can confirm that this new function, which is built by adding together two known solutions, is itself a solution of our original differential equation. Here I've taken the appropriate derivatives of y sub 4, plugged them in on the left-hand side here of my original differential equation, and then after some simplification, sure enough, everything in that left-hand side cancels out, and so it does equal 0. So the original differential equation is satisfied. So we have two key principles here. First, from note 1, we see that any scalar multiple of a solution is also itself a solution. And then secondly, from note 2, we see that the sum of two solutions is itself a solution. So I'll take y1, multiply by a constant, say c1, same thing for y2, then I'll add those together. It turns out that this is the general solution of this differential equation. There are some details that we need to discuss, and we will later formally confirm that this is in fact the general solution. But for now, as we're getting our first exposure to this type of ODE, trust that the process that we just followed, which was we found two distinct solution functions, y1 and y2, we multiplied those by constants, we added those together, that process does yield the general solution. And then I will just note in passing that this is related to the idea of a linear combination of basis elements from linear algebra. If you have not taken linear algebra, don't worry, I'm not going to get into it too deeply here, but if you have taken linear algebra, this is one of several places where we will borrow ideas about bases, about linear combinations from that course. At the top of this next page, we formally state the facts we just identified in Note 1 and Note 2. Theorem 1 states, if y is a solution of a linear homogeneous ODE, then so is cy for any scalar. Note 1, as you recall, said that the scalar multiple of a solution is also a solution. Theorem 2 states that if y1 and y2 are solutions of a linear homogeneous ODE, then so is y1 plus y2. It's worth pointing out that these theorems apply to any linear homogeneous ODEs. Our examples have constant coefficients, but that need not be true in order to apply these theorems. And it turns out the method we just demonstrated is really all there is to solving LHCC differential equations. Almost. We will follow this procedure. We will assume our solutions have the form y equals e to the rt. We plug in that function along with the necessary derivatives, solve the resulting equation for r to identify which value or values of r make that function a solution to our ODE, and then we build a general solution by taking the sum of scalar multiples of our individual solutions. That technique is outlined in this paragraph here. There will be details that arise that complicate things, but for now, this is the entire method. Let's try another example. Example 1. Our ODE is y double prime minus 3y prime plus 2y equals 0. And this time we've been given two initial conditions. Y of 0 equals 2, y prime of 0 equals 6. Recall that the general solution we built in the previous problem had two distinct unknown constants, c sub 1 and c sub 2. As such, we will need two initial values in order to uniquely solve for those two constants. In this problem, notice that we've been given an initial value for y. Think of that maybe as an initial position, and also an initial value for y prime. Think of that as like an initial slope or maybe an initial velocity. So let's imitate the procedure we used in the first example. First, I've assumed that my solutions have the form y equals e to the rt. I found the appropriate derivatives and plugged those in to my differential equation. Next, I'll do some simplification. And as in the previous example, I know that this exponential out front cannot equal 0. So the solutions to this equation will result from setting this quadratic equal to 0. Once again, my quadratic factors nicely, and so I can pretty readily identify the two roots of this quadratic equation, namely r equals 1 and r equals 2. And then I can combine these in the way that we described in the previous example by multiplying each of the resulting solutions by a constant and then adding those two together. And so my general solution will be c sub 1 e to the t plus c sub 2 e to the 2t. And then I just want to point out, I know this is the second example we've done, but it seems pretty clear that the fact that I've ended up with a quadratic here, and specifically the quadratic, which has the same coefficients as the left-hand side of my differential equation, doesn't seem like an accident. I'll talk more on that in just a second. But anyways, so now that we have this general solution, go back to the stated initial conditions and incorporate those. Notice that in order to incorporate this second initial condition, I will need to calculate the derivative of my general solution. That seems pretty straightforward. Here on the right, underneath my general solution, I went ahead and calculated its derivative. And then over here on the left, I've plugged in the given initial conditions. We're told that if we plug in t equals 0, which I've done here, plugged in t equals 0 into my general solution, the result should be the value 2. And then if I plug t equals 0 into my first derivative, the resulting value should be 6. This yields a little system of equations, two unknowns, two equations in terms of C1 and C2. You can use whatever technique you're most comfortable with, substitution, elimination, to just continue to the necessary algebra to be able to solve for C1 and C2. Not surprisingly, I've kind of run out of room in doing my calculations. Here I chose to subtract these two equations. So I just took the first equation minus the second equation, and then that led pretty directly to the fact that C2 equals 4. Plugging that into my first equation tells me that C1 equals -2, and then that yields the actual solution, which I've put in this green box right here. That's our final answer, and so we're done with this problem. I do want to just make one note, because oftentimes in the contexts that are being modeled by these types of differential equations, our goal is to understand the end behavior of the solutions to the differential equations. So I just wanted to speak briefly in terms of the limit of this solution as t grows without bound. There's sort of a conflict, because this exponential will grow infinitely large, and its coefficient forces it to grow negative and infinitely large. So we kind of think of this first term as going to negative infinity. The conflict arises because the second term appears to be going to positive infinity. The exponential will grow without bound, and it has a positive coefficient. So who wins? Which of these two exponentials dominates if we've got the one that's going to negative infinity and one that's going to positive infinity? And the key factor here is the coefficients on the exponents. So in my first exponential, I just have a positive 1t in the exponent, whereas in the second exponential, I have 2t. So this second term will dominate, and so the limit of this solution will be positive infinity. I didn't really have room to write that near my solution, so I've written it over here kind of in the left margin. Cool. At the bottom of the page, I have a couple concluding remarks. First, as I mentioned during that last example, it is no accident that we ended up with a quadratic equation in both of the above examples. And it's no accident that that quadratic equation has the same coefficients as the business side of our diffie-q. This is a general principle. So here, I've indicated that the polynomial that's associated with the differential equation has a name. It's called the characteristic polynomial. So moving forward, in the name of efficiency, you'll see me go straight from the differential equation to the characteristic polynomial. That's always going to be our first step. And then this last paragraph foreshadows the quote-unquote glitches that could potentially derail the process we've used in this lecture. Specifically, we know that quadratic equations can have different types of roots. We could get real distinct roots, as we did in the previous two examples, and that's actually the basis for the title of section 3.2. Section 3.2 is called Real Roots, and the author is specifically referring to the process that we've outlined here being applied in the case where we get real distinct roots, as we did in this example. But as you know, this isn't always necessarily true. We could have a quadratic like r minus 1 quantity squared equals 0, which only has a single root, which is repeated, the root r equals 1. It's repeated twice. Or we could have a quadratic like r squared plus 1 equals 0, which has imaginary or complex roots. So what do our solutions look like in those cases? Stay tuned. In upcoming sections, we'll answer those questions.